So, hello everyone, thanks for joining the presentation. This is Ezpeleta, third from the left here, and these are my colleagues from the Automation and Control Lab at the National University of Rosario in Argentina. Today I'll be talking about a small but hopefully interesting educational project that we have going on at our lab, about the development of a lab scale, I'll probably hide this, a micro smart grid with renewable sources and energy storage, and possibly the most interesting part as far as this conference is concerned is that the grid has been developed or is being developed rather mostly through final electronics engineering projects. So essentially this is a brief agenda for the talk. We'll see a very brief description of the smart grid. We will talk a little bit about how students participate in the development of the grid. Then we'll see some examples, and then we'll jump to the conclusions. So very briefly here, unfortunately I don't have time to go into detail, but this is the planned architecture for our smart grid. It's organized here into hierarchical, fairly standard field control application supervision level. We have several communications protocols being used here. CAN, maybe some commercial protocols such as Profibus, Ethernet, and so on. And from the point of view of the electrical topology, we have a 300 volt DC bar on the bottom left here. We have on the center an AC bar, and then on the right we have a 380 three-phase AC grid, which is connected to the utility grid. And from the point of view of the equipment here, we have a photovoltaic panel array with boost converters. We have a wind generation system with an emulated wind turbine, so that this is not a physical turbine, but a machine which is controlled to behave like a wind turbine with variable parameters and conditions. That drives an asynchronous generator, which is then rectified in controlled manner into DC. Similarly, we have a second wind generation system, a larger one. This is 20 kilowatts. This is maybe 1.5 kilowatts. And in this case, we use a synchronous generator. And well, as I said, we don't have time for too many details, but these boxes here are our generators and the network. Then we have some storage. We have a battery bank. We have a flywheel storage system, which is a mechanical battery of sorts. We have also supercapacitor based storage, so fast storage, high power, low energy storage, and with their corresponding converters here. And the battery bank is directly connected to the DC bar. Finally, obviously, we have some loads, some consumers. We have consumers in the DC part of the grid. We have a nice programmable RLC cabinet with controlled by solid-state relays with switch load to produce stepwise variable load in R, L, and C, and that's controlled by a PLC here. And then we have some standard AC loads, some educational equipment. We have some pumps there, and possibly with variable speed. Okay, so these are standard AC loads. And finally, we have some interconnection between the the voltage levels. In this case, we have two-way converters which link the AC and DC parts of the network, and then on this end we have a contactor which possibly connects the internal AC grid with the utility grid. This is so before was, as I said, the planned architecture. This is what is currently operational. So you can see here the flywheel wind generator systems. We have the a CAN network connecting all of them so that they can be operated from a computer. And okay, some of the components here are shown in dashed lines. Those are currently in development. So moving on to the most interesting possibly part, as far as the conference is concerned, we'll see how it is that students participate in the development of the grid and why we think this has been a successful, interesting educational experience. So basically, as a standard part of the electronics engineering curriculum, students have to complete 3 courses. Engineering and project management is mostly about basic theoretical tools about project management. Then project 1 is basically about proposing a problem and a possible solution to that problem without doing any hands-on work on that. And then on project 2 they move on to the actual execution of the project. They build prototypes and do some verification and testing, commissioning, etc. So how do we come into play here, and what is this educational experience that we've been talking about? So what typically happens is that if you let students choose their own problems, they will typically do very different sort of things and mostly atomized, very diverse things like building drones and that kind of thing. So we felt that while that was very interesting for the students, it wasn't really being integrated into something that would be interesting for the university community as a whole. So our idea was to start proposing topics within the context of this smart grid, so that the projects that the students developed would form part of a larger a more continuous project. So the way we take part in this is we propose topics, as I said, and then we provide them with a physical environment, including tools, instruments, etc. And then we also typically offer funding for buying components and such, and we offer technical and academic guidance during execution. And okay, moving on to some of the educational advantages, why we feel this has been successful. Firstly, the fact that they take part of a larger project, in this case the microgrid, allows students to not only focus on the hardware level, which is what they typically do, but instead gain a more systemic understanding of how that hardware makes part of a larger whole. Then in connection with that, or expanding on that, this sets boundary conditions for them, so they need to learn how their individual component interacts with the whole system. So they learn a lot about interfaces and how different systems connect, both in from the point of view of electrical connection, voltages, impedances and such, and also from the point of view of communication. then it encourages, this is very important, it encourages students to communicate with each other. Okay, so project teams are typically very small, maybe 1 or 2 students, and they don't, if they build a drone or something, like I said before, they don't really interact with anyone else, and so projects end up being very, very isolated. Finally, this motivates them to produce solid documentation and to interact with others, as I said. So to produce and to read documentation. Expanding a little bit on that, this is the documentation that we typically ask for. So a copy of the project, obviously, for electronics, PCB layouts. So I know it's written here. I won't go into detail, but you can imagine. Okay, it's a lot of documentation they produce, and we feel this is very important for them to develop as engineers. Okay, a good deal of being an engineer is about being able to write and read documentation, and not only developing hardware. Okay, so moving on to the conclusions, we have a little time left. The takeaway here is that we have a project where students directly participate in the development of an experimental smart grid, and they do that through their final engineering projects, rather than doing individual isolated projects. So you can see here some of the skills that student participation involves. Students learn by doing. This is very important. They build actual working equipment, but they also contribute to a long-term project, so that they are part of something larger. They have to understand the full system they are working with, not just their individual small PCB in isolation, but how that interacts with other systems. And within the particular moduli, they developed, build, they commission, and they document, as we said. They also are physically present in the lab, which is, we feel, important for teamwork and for communicating with professors and with other students. They also occasionally, or usually rather, participate in writing small conference papers, technical papers, and they, as far as possible. And finally, to wrap up, these are some of the specific contributions in terms of educational that we see on the students. We mentioned some of these before, but overall we think that it has been a tremendously positive experience for students. We really see a progress from the time they come to the lab for the first time, and when they actually complete the projects and graduate. And we also think that from the point of view of the university community as a whole, it's tremendously valuable, because in typical electronics engineering projects, students graduate, and then to a large extent their projects are forgotten, and they're not continued and carried on by anyone else. While in our case, we feel that there is a true continuity between each cohort of students that come on and work at the lab. So we hope this is maybe an inspiration to some of you who might be in a similar situation, and we really think this is a win-win situation where students learn a lot. They get very interesting projects to work on, actually meaningful projects which are embedded into something larger, and at the same time, obviously, we get the benefit that we can move our microgrid project forward with the help of students. So thank you for listening, and I hope you have enjoyed and hopefully drawn some ideas from this to apply in your own labs and faculties. Thank you very much.